Welcome back everyone. So in the last lecture we have seen that means what are needed, that means like the RTL file and then the corresponding library file and then the constant file. Okay, these are the inputs to the design with compiler, and there are several compilers like power compiler, library compiler, and then HDL compiler. There are several compilers which compile all this information, and after compiling all those informations, and then it produces the corresponding get level netlist for the, that means input logical expression. Okay. So now we are going to, that means describe what is the, that means high level design synthesis flow. Okay. So that means in the high level design flow, it starts with the HDL design entry. Okay. So what is HDL design entry? HDL design entry means whatever design you are, that means intending to that means perform. Okay. So write that into or describe that into using any of the HDL language. Okay. So whenever you are doing that, a good coding practice can facilitate you for a successful that means synthesis technique in that means it can cause a that means low complexity, or it can take a low compilation time whenever you are using it in design compiler. So after doing that, that means after compiling it in design compiler, then that means after writing the HDL code, what you can do, you can just pass it on to this design compiler tool. So after in design compiler, you have to perform the two things, that means in parallel, which is in design exploration as well as that means that functional simulation. So why I need functional simulation and why I need this design exploration. So design exploration, that can be done, as I said, design exploration can be done through DC Explorer. So DC Explorer do what? DC Explorer can be used for implement any specific design goals such as design rules or optimization constants. It detects the mismatch and missing constant, as well as it resolves those constants, that means those problems. And you also can create, as I said, that means in the early lecture I said that in DC Explorer you also can do this, that means floor planning, you also can manage the, that means routing, you also can manage the, that means placement, all those things you can manage, so that the design, that means whenever you are exploring the design, so at that time your constant that can meet, though you are not doing this full synthesis, or you are not doing the, that means full actual implementation of the corresponding design. So you can do. So if that means if it is not meeting, so whenever you have done, or you have, that means performed the design exploration, so if it is, that means whatever results you are getting, if that is fails to meet with the 10% of your that means desired specification, so at that time it indicates that again you have to go back to your architecture, or you have to go back to the HDL code, so that you can change it, you can change the architecture, or you can change the methodology, or you can change the code to get the specification to be that means converge, okay, or to match. So in functional simulation, basically we do functional simulation to check whatever code I have written, so that is working function, that means properly. That means the function which I am trying to implement, like if I want to design an adder, okay. So whenever I have written the logical expression for an adder, so at that time I have to perform, so I can make a mistake whenever I am writing the logical expression, so at that time I can make a mistake. So at that time, if I am making any mistake, so at that time using functional simulation only, I can see, or I can visualize that, okay, there it is not acting as an adder, it is acting as something else, okay. So at that time, using this functional simulation, I can check whether that logical expression or logical function that is working as the desired function or not. Okay. So if it is not meeting, again there is that, okay, if it is meeting, if it is working fine, then it's fine. If it is not meeting, so at that time what I have to do, again I have to go back, I have to, that means I have to change the HDL code, and again I have to perform the both, that means I have to repeat both the design exploration as well as functional simulation, unless and until it is meeting with the original one or the desired one. Okay. So after, if it is that means everything is fine, that means design exploration is fine, and then functional simulation is fine. So at that time you perform the design implementation synthesis by using design compiler to meet the corresponding design goal. So after synthesizing the design into a get level netlist, verify the design which is whether that is meeting your goal. That means, so now logical expression that has been now converted into the get level netlist. So during the that means conversion, or during this translation from expression to the corresponding get level netlist, if there is any discrepancy has been happened or not, that again I have to find out. Okay. So that means now I will check its functionality with the corresponding get level netlist of it, not the functional level implementation or functional level description which has been described to any HDL. Okay. So again, if the design does not meet your goals, that means whenever I am working with the netlist file, if the design does not meet my goals, so at that time again generate and analyze various reports to determine the techniques you might be used to correct the problem. So that means again at that time I have to use any other technique, like there are several, that means performance enhancement of that means techniques, like as I said, that pipelining, then register retiming, then clock gating. So these are the techniques which that means used to enhance the performance of the circuit. So that kind of circuit at that time that will be incorporated into your design, and then again I have to go back, that means I have to follow the same process, like I have to again design export, and then I have to do the functional simulation, then again with the netlist file again I have to do all these things. Okay. So after doing this, okay, after getting the netlist file, if it is working fine, so at that time I can go further with the physical implementation using the IC compiler tool. So whenever after that means IC compiler tool, I will get the that means GDS file, geometric description file of my circuit. So again I have to back annotate those data, like I have to back annotate like the power information, timing information, and this area information, all those data that can again, so like that means for any path, for delay calculation I need this resistance information, capacitance information, that means for net delay, for gate delay, and then path delay, all those delay information I need, which are basically varying the length of that means net, or the resistance capacitance associated with those nets, that are basically important whenever I have performed this that means physical implementation of my circuit. So those data again that will be back annotated, those information, and again it will be passes to the corresponding that means timing analyzer tool, or this this functional simulation, that means this simulator, logic simulator, or any other simulator, so that every aspect the design is intact, that means the functionality of the design that is meeting the specification and it is performing well, functionality of the design that is also well. So all those things I have to check by back annotating those information, and again I have to run those in this tool set. Okay. So if the results do not meet design cycles, then again I have to go back to the that means step 3, which is that means the design synthesis using design compiler. If everything is fine, then my design cycle is completed. Okay. So there are different terminology which are associated in this course. Okay. So the course, that means in this basically this lecture, that is design compiler. So the design terminology, first design terminology is that synthesis. I am using this term from the beginning. So what is synthesis? Synthesis is the process that generates a get level netlist for an IC design that has been defined with a hardware description language. And synthesis includes reading the HDL source code and optimizing the design created from that description. Okay. So that means whatever logical expression I am giving as an through this HDL code, that will be converted, or that will be described now using the basic gates. Okay. So that is the basic of synthesis. Then what is optimization? I am talking about optimization. So what is optimization? Optimization is the step in the synthesis process which implements a combination of library cell that best meet the functional, timing, area and power requirements of the design. So optimization, when I have to perform the optimization, suppose for one circuit the specification is, that means is with, that means not that much, that means stringent. So at that time very easily I can achieve my specification. So at that time I don't need any optimization to do, that means in the first iteration or in the second iteration if I got my specification to be matched, so at that time I don't need further optimization of my circuit. If the specification is stringent enough and it is not meeting after 2, 3, 4 or 5 iteration, so at that time I have to do, that means in each of the iteration I have to perform the optimization, and so that I can meet the specification, stringent coefficient specification of timing, area and power. And then again design compiler. So here we are doing the compiling. So what is this, that compile? Compile is the design compiler process that executes and the synthesis and optimization steps. That means I can perform this synthesis and optimization through this compile mode. And after you read the design and perform other necessary tasks, you run the compile ultra or compile command to generate a get level netlist for the design. Okay. So these are the terminology which are associated with this design compiler. Then I have talked about that there are that means design methodology. So what are those design methodology? That is, one thing is that flat design, another thing is that hierarchical design. So what is flat design? The flat design contains no sub design. It has only one structural level. That means there is no sub blocks. Only one module contains the whole description. That means in those particular HDL file, it contains the whole description of the circuit. Okay. So that is flattening of the design. Okay. They contain only library cell. In hierarchical design, they contains one or more design as sub design. That means there may be more than one module. There may be some other sub modules also. So each sub design can further contain sub design and create multiple levels of design in hierarchy, so that the design can contain sub design are called the parent design. Okay. So then the compilation that can be done in two ways. Another one is that full compilation, another mode is incremental compilation. So what is full compilation? During a full compilation, the design compiler maps and optimize the entire design, resulting in a get level netlist of the design. So any mapped cell are unmapped to their logic function first. No number of attempt is made to preserve existing netlist structure. Okay. So that means in full compilation mode, in one compile the whole design has been compiled and that means optimized. In incremental compile mode, that means it improves this quality of results. That means first it do this initial compile. That means here that compilation has been done in steps. Okay. So incremental mapping basically uses the existing gates from an earlier compilation as a starting point from the mapping process. So it improves the existing design cost by focusing on the areas of the design that do not meet constant and affects the second pass of the compile. The existing structure is preserved where all constants are already met. Mapping optimization are accepted only if they improve the circuit speed or area. That means in the incremental compiling mode, so you are doing, that means suppose one block is already that means it is meeting all these constants. So it will take those library and it will try to implement those optimized way for redesigning, or that means recompiling the other design too. So this is incremental compiling mode. Okay. So this design compiler which supports this following the compiler flows, that is, in topographical mode you can perform this second pass incremental compile to that means you can do this, or for DFT or for DFT max also you can do this. Okay. And each of this basically we use incremental compilation mode to improve the quality of results. So whenever we are compiling, so at that time there are various strategies or there are various that means techniques. One thing is that top down compile mode. So that means it takes the top level design and all its sub design are compiled together. In the bottom up approach, the individual sub design are compiled separately, starting from the bottom of the hierarchy and then proceeding up through the levels of hierarchy until the top level design is compiled. So in mixed compile mode, you can take advantage of both the benefits of that means top down approach as well as bottom up approach by doing this in the top down compile strategy for smaller hierarchical of blocks and bottom up approach for that means to tie up those smaller hierarchical block into to create a larger block. Okay. So these are the various strategies for compiling in design compiler. So we have already discussed about this optimization. So optimization that can be done in 3 levels. One is architectural level, another one is logic level, another one is gate level optimization. So in this 3 level I can do this optimization. So as I said that means there are several other modes of design compiler, which is like this DC underscore cell, then in topographical mode it will be DC underscore cell, then hyphen topographical mode, then I have to use multi mode or multi corner mode or multi threshold mode, and this UPF mode is that is for low power mode, that is unified power format mode. Okay. So whenever we are trying to design a system, that means the system if it is particularly intended for low power design, so at that time we have to use this UPF mode. That is not considered here in this course. Okay. So but there is the option which you can opt for. So in the synthesis flow, it has that means it has started with you have to that means first you have to develop the HDL files, then specify the libraries. So there are several comments in the design vision which are associated to load the library or to that means connect the library to the design compiler. So such as link library, target library, symbol library, synthetic library, create that means MW library or Milky Way library. So after importing those library into the design compiler, then you can do the reading the design, that means reading the Verilog file. So in the reading Verilog file, you have to perform this analyze, elaborate, all these things you have to do. So after that again you have to like define the design environment. Define the design environment means that means you have to put the constant file. The constant, where from you will get the constant file? Basically constant file is the representation of your specification. Okay. So whatever, like if I said that okay my design should be run on 100 megahertz. So the clock frequency that should be like 10 nanosecond. Okay. So now I will put that okay clock that cannot be more than 10 nanosecond. Okay. So that is constant to the design vision, that okay that clock period will be set to 10 nanosecond only. So after that like there are another thing, that select compile strategy. So whenever that means after setting all this constant file in the design vision for like for timing, for power, for area, all this constant I set. So after that I have to select the compile strategy. So compile strategy will be either top down or bottom up or mixed of that. So that means there are effort level. So you can choose like high, low and medium. So whenever you choose high, so that's at that time it uses DC Ultra, and again DC Ultra provides what? DC Ultra provides the advanced optimization technique for each of these. Okay. So that's why you have to select this select compile strategy for compiling in design compiler. So after doing the synthesis and optimizing your design, you have to analyze and resolve. So whenever you are doing that means analyzing your circuit, the corresponding netlist file. So if any problems comes, so you have to resolve those problems, and if everything is fine, then you save the design into the database file. Okay. So this is the synthesis flow. So before the synthesis, you have to prepare your design. Okay. So for preparing your design or the constant file for the synthesis, you have to do this managing the design data, partitioning you have to do for synthesis, the HDL coding, good HDL coding you have to do for synthesis, you have to perform the design exploration, you have to create the constant file, you have to, and parallel to that you have to do the functional simulation too, which has not been, that is not at all part of this, but you have to do this logic, that means functional simulation of your circuit, that also you have to do. So I said that okay, managing the design data. So at that time you have to control, either you have to do, that means this controlling of the design data, or you have to organize the design data. So organize the design data means the design source code that may be with this extension, that will be with .v for Verilog, .vhd for VHDL. The synthesis scripts. Synthesis script means for they are putting all this information, that means all these comments to the design vision in either in .con or .scr. Okay. Then the reports, that means for analyzing. So by seeing the reports only I can analyze, right? So the for analyzing the reports will be like done with the extension of .rpt or .log, and after that I have to save the final data, that means final design. So the final data will be saved in .ddc format. This is synopsis format. Okay. So and this is that means design, how you can manage your design. Okay. So after that, what I said, that partitioning I have to do for synthesis. So partitioning, how I can do for partitioning? So partitioning for design reuse. So design reuse decreases the time to market by reducing the design integration and testing effort. When reusing existing design, partition the design to enable instantiation of the design. So what does it means? That means reuse of the design. That means suppose once, so one multiplier is used in FFT, that same multiplier that can be used for like DCT or like for any other transform like DWT. Okay. So that means if once I have done or I have completed each of the, that means each of the things, each of the synthesis part, that means the function simulation and then design exploration and then synthesis, everything I performed. Okay. So again, to do that again for whenever I am using those particular multiplier block in DWT, so that is unnecessary. So it will take too much of time to redo those things. So here what you can do, I can reuse those design into the for other design. So that I can do. So here in design compiler, that option is there that you can do. So to enable the design to be reused, follow these guidelines during the partition and block design. Thoroughly define and document the design interface, standardize interface whenever possible, parameterize the HDL code. So again, so how, that means when I can reuse. Okay. When I can reuse, that means the corresponding function needs the multiplication operation, but the specification that might be changed, that will not be same for the requirement of DWT or for the requirement for the FFT. So the requirement of that requirement means that either that means the coefficient for that will be changed, or that means the input operand that is changed, or the corresponding bus width that is changed. Okay, so that's why whenever we are designing the multiplier or the complex multiplier, if I say, so that multiplier will be, whenever I am describing it through HDL code, it will be parameterized. That means that bus length that will not be hard defined. So it will be defined by a parameter only. So for DWT, if I am using like 16-bit, and for FFT if I am using 32-bit, so I will just declare that, okay, define the bus width as 32-bit for DWT, 32-bit for FFT, 16 for DWT. Only that, by doing that I can do. So that means the code will be parameterizable, so that I can easily reuse the corresponding multiplier block for designing the two things, DWT as well as FFT. Okay, and the standardized interface is needed because the input output will be connected with the corresponding other blocks. So again, the standardized interface should be used, and properly documentation. Otherwise, suppose another person is using those as a IP if they are using, so at the time if the proper documentation is not there, that means if that is missing, then he will not get much information about your design whenever he tries to reuse that. So that's why proper documentation of those circuit which will be reused in future, that is very much needed. Okay, so then keeping related combinational logic together, that means all the time we know that suppose two blocks are very much that means interconnected or interrelated to each other. So at that time, whenever they will be placed, so at the time to reduce the corresponding path delay between them, so that means as there is so much of that means influence between these two blocks, so at that time they will be always they will be placed or they will be kept together. Okay, so that's why you see that this group related combinational logic and its destination register together. Design compiler has the flexibility to merge logic, resulting in a smaller, faster design. Grouping combinational logic with its destination registers also simplifies the timing constant and enables sequential optimization. Another point is that eliminate glue logic. So what is glue logic? Glue logic is the combinational logic that connects blocks. Moving this logic into one of the block improves synthesis results by providing design compiler with additional flexibility. So eliminating glue logic also reduces compile time because design compiler has few logic levels to optimize. That means now glue logic are the blocks, that means they are the blocks which are fully combinational. Okay, and they are basically used for connecting between, they act as a connector between two other blocks. Okay, so if they are basically, if we as a designer, if we put more of that glue blocks into our system, so at that time it creates, or it that means needs more compilation time than the reduced one. Okay, so that means at that time what will happen, the design compiler, that means if I put those glue logic, so at that time the level of optimization that will be increased. So if we remove, that means if we use least number of glue logic, which are, that means very much only if it is useful, then only I will use. So those glue logic will be very much like helpful for further optimization in design compiler. Okay, so then again we can do this registering the block outputs. Okay, then that means the output that will be registered, and then partitioning by design goals. That means each of the block specification, like the adder design and the multiplier design, that means the corresponding performance of these two blocks, that is different. So let's consider another example, like I have one multiplier block and I have one like decoder block. So the complexity of that two block is totally different, and then design goal, that means now it will be totally dependent on the performance of the multiplier block. Okay, so that's why we have to partition the corresponding blocks in such a way. It is, I am just telling that in a simpler way. So whenever we are talking about system on chip, so at that time each of the block, that is not at all only that means multiplier, it may be a FFT, and then it may be a DWT, it may be a that means baseband modem corresponding IPs, all those things. So at that time we have to partition each of these blocks by design goal, so that the whole design specification that matched accurately. Okay. So for today, I think for today's lecture, this is it. So again we will come, that means we will continue this lecture in the in future lecture. Okay, thank you.